Hello everybody. Today I'd like to go through some questions on continuous random variables and probability density functions. So with a continuous random variable, we need to have some kind of density function, and we'll find probabilities by finding areas under the density curve. So our density function is some kind of function, and we find probabilities of a particular event by areas under the curve. So there are certain things that have to be true, or it couldn't possibly be, or it wouldn't be a density function. Probabilities can't be negative, so the areas under the curve can never be negative. So our density function, which is continuous, can't be negative either. Our density function has to be greater than or equal to 0 everywhere. And the other thing is the area under the curve has to be the probability something happens. So the area under the curve has to be 1. Okay, so the area under here has to be 1. Usually we do that by saying that the integral of the density function is 1, but we need to find the area somehow. Somehow the area is 1. Integration's often a really useful technique. So the first one I want to look at is this one, which is an example of a uniform distribution. This is a really useful distribution in probability and statistics. It's what we use when we're generating random numbers, but later on, if you do statistics further on, you'll discover it's a really useful distribution theoretically as well, and it's a really straightforward, simple one. Uniform, of course, means flat. This is a flat distribution. So what is it? We've got two real numbers, a and b. A is less than b. Because a is less than b, we have that b minus a is greater than 0. Okay. Now our density function is 1 on b minus a just when x is between a and b, and it's 0 everywhere else. First thing we need to do is to check it's greater than or equal to 0 everywhere. Well, it's 0 here and here. Well, because b minus a is greater than 0, 1 on b minus a is greater than 0, so fx is greater than or equal to 0 everywhere. First thing we have okay. Next thing we need to do is to check that the integral, the area under the curve, is 1, and also graph the function. It's a really good idea to graph it next. See why it's called the uniform distribution. So somewhere on our x-axis we have a and b. And what's our density function? Well, between a and b, our density function is 1 on b minus a. So it's a straight line. It's uniform between a and b. But otherwise, in other words, when x is less than a or bigger than b, our density function is 0, which I will try and indicate here. Okay, there's our density function, and you can see it's always greater than or equal to 0. The next thing we need to show is the area is 1. Well, the area under the curve is this area here. We need to show that area is 1. And you can integrate it if you like, but it's just a rectangle, so the area under the curve is more easily found just by saying this distance here, from here to here, that distance there is b minus a, and the height is 1 on b minus a. Which is 1. So it's positive everywhere, the area under the curve is 1, and we've got a nice graph of what it looks like. The next function I'd like to look at is this one, the Pareto distribution. And for this it involves a k. K has to be positive, but it could be any real number. So for any number, you get one of these distributions. There's a whole infinite family of distributions here. And the density function is k on x to the k plus 1 when x is greater than or equal to 1 and 0 otherwise. We need to do these three things to show that it is a probability density function. Okay, so first off, to show that it's always greater than or equal to 0, well, it's 0 a lot of the time, and the rest of the time, when x is greater than or equal to 1, it's k on x to the k plus 1. Well, k is bigger than 0, x is bigger than 1, so this is always bigger than or equal to 0. So to start with, we have, for x greater than or equal to 1, we get that k on x to the k plus 1 is greater than, is in fact greater than 0. Okay, so this is always bigger than 0, and this is 0. So fx is greater than or equal to 0 everywhere. Okay, so the next thing we need to show is the area under this curve is 1, and I suggest we sketch the graph of the function first. So what does this look like? Let's draw it in this little box up here. Okay, here's our x-axis. The density function is going to be 0 when x is less than 1. So we need 1 here. So our density function is 0 here. And what happens at 1? When x is 1, our density function is going to be k on 1. And then when x is greater than 1, it just decreases. So the only thing the density function can look like is that. Okay, so there's our density function. The next thing we need to show is the area under this curve is 1. And I can't think of any way of doing this but integrating. So we need to integrate this and show we get 1. So finally, we need to integrate this. Well, our density function is 0 up to 1, so that's just the integral from 1 to infinity of this function, k x to the minus k plus 1 dx. Now, integrating to infinity, of course, what we really do is we integrate as far as r, say, and then look at what happens as r tends to infinity. So that's going to be the limit as r tends to infinity of the integral from 1 to r of k e to the minus k plus 1 dx. Okay, and this is a very, x to the k plus 1, x to the k plus 1. Momentarily, it didn't look quite as straightforward as an integral as it usually is. Okay, integral of k x e to the minus k plus 1 dx. This is going to be the limit as r tends to infinity of, and when we do this integration, we're going to get x to the minus k minus x to the minus k, evaluated between 1 and r. So we're substituting in x from 1 to r. And this is going to be the limit as r becomes infinity of 1 minus r to the minus k. And what happens to this as r tends to infinity? This becomes 1. Thank you.